Okay, so thank you, Fabien, for the nice introduction, and hello, everybody. So I've already had very nice discussions with some of you, but nice to meet you all here. So as Fabien said, I will present my work around several steps of the knowledge graph lifecycle, construction, refinement, applications, with always a neuro-symbolic perspective, which is something I try to develop in every one of my work, especially through two new national research projects in France, Ecladata, with I'm the PI, and 82TA with I'm the one work package leader. So first, a bit of context, but I will be very quick on it because of the theme of the Wimmics team. So how I see knowledge graphs in the web of data, and especially how I consider them in my work. So I see them as directed and labeled multigraphs in which nodes can be of different broad types, individuals, classes such as writer, person, literals, and edges link several nodes and are labeled by a predicate which indicates the nature of the relationship holding between two nodes. So these graphs are multigraphs because several edges can hold between the two same nodes. The main interests for my work in these graphs of the web of data are the deductive reasoning that is available because of the logic-based foundation. And especially, for example, knowing that Alice is of type writer and writer is a subclass of person, we can deduce that Alice is of type person. And so these form of reasoning available on knowledge graphs will be intertwined with other forms of intelligent processing in my works. So we can have a general assessment about the web of data. First, there is an increasing volume of available data in various formats, so databases, tables, especially in open data portals, texts, and so we can automatically extract knowledge to build knowledge graphs, which leads to an increasing size and number of available knowledge graphs. For example, on the LoudCloud repository, where each circle on the right represents a knowledge graph. So we can see that between 2007 and 2020, there has been an explosion in the number of available knowledge graphs. The standards of the semantic web allows for the concurrent publication and edition of knowledge graphs, which leads to potential overlaps between them. Also, automatic knowledge extraction approaches lead to knowledge graphs that are never complete or correct, and so there is a huge interest in completion and correction methods. For example, link prediction. Because knowledge graphs are expanding in size and numbers, we can also mine them to discover new and useful knowledge units, which can then support various applications. So the most well-known is search, but we can also think about question answering, recommendation, and explainable AI. So these are the steps of knowledge graph lifecycle that I consider in my work, with some issues, some challenges. For example, heterogeneity in terms of vocabularies or granularity of representation, scalability because of the increasing size of knowledge graphs, and also with the perspective of studying the interactions between deductive reasoning and other forms of intelligent processing. So my research broadly revolves around all these steps, and the purpose of this talk is not to present everything, but just to focus on one example in each step to build somehow a consistent pipeline from construction to refinement and applications, every time illustrated through neuro-symbolic interactions. So let's start with knowledge graph construction, and especially with the bootstrapping of an enterprise knowledge graph with Wikidata. So there are several knowledge extraction approaches from text or from tables. So for example, at Orange, I've worked on the Dagobah algorithm, which allows to automatically extract knowledge from tabular data. But such approaches require an existing knowledge graphs to have some business entities and relations to detect in the raw data, which of course poses a problem when the bootstrapping knowledge graph is empty. And so there is a need to bootstrap knowledge graphs, especially in business case with business domains and business entities of interest. What we did at Orange, and what we proposed, is to use Wikidata, so a large collaborative knowledge graphs covering several domains, so a broad spectrum, and to focus it on some specific business domains of interest to Orange, thanks to an internal repository which is called Dicopedia. So to illustrate what is Dicopedia, well, it's a wiki where we have some repository of terms, sometimes associated with a few words definitions. Some of these terms can be public term, for example, big data, and some other are internal and you've never heard of. And the idea was to say, okay, we can bootstrap the knowledge graphs by using public terms to have some public knowledge about business domains of interest. So to do that, we thought of linking public term with their equivalent in Wikidata. So for example, here, big data. And then to expand a bit the knowledge graph, do a hierarchical expansion along the class hierarchy of Wikidata. So for example, moving from big data to programming paradigm, and then to paradigm, and so on. So the pipeline becomes as follows. We have Wikidata, we have Dicopedia. We use a semi-manual mapping to have a list of seed entities from which we perform the hierarchical expansion to build the EKG nucleus. So let's try that out with a small number of seed business QIDs, so 800, and we already have more than 2 million subclasses and 4 million instances, which is far too much for a nucleus. Plus, we have a deviation from the original business domains. So to illustrate, from Microsoft SharePoint, we were able to retrieve human, galaxy, and stars, which clearly deviates. So sure, it's not perfect, it's Wikidata, it's collaborative, and so we need to find some pruning mechanism. And what we wanted to test is not degree, because, well, it's very usual, and also the distance in the embedding space automatically learn to perform some link prediction task, but to use the distance as a pruning signal. So graph embedding, what are they? Well, they are the transformation of graph structures, for example, nodes or predicates, into a d-dimensional space, so vector space, that preserves as much as possible graph properties. So nodes, predicates, or subgraphs can be represented as vectors. But is the distance in the embedding space a thematic similarity measure? Well, it is not proven, and so we wanted first to test this hypothesis. Are two classes thematically distant also distant in the embedding space? To test the hypothesis, we needed to compare the distance in the embedding space with some thematic reference, which we considered to be the hierarchy of Wikidata. So we know the hierarchy is not perfect, and obviously that's why we need the pruning mechanism. But still, we wanted to be able to find some association between distance in the embedding space and distance in the hierarchy on the good part. We tested two definitions of what should be the distance in the embedding space. Distance D1 being the usual definition, so distance between the embedding of the starting QID and the class, and distance D2 being the distance between the centroids of their instances. And these are the results we got. So between each pair of classes, we measured the number of hops in the hierarchy and the distance in the embedding space. And we can clearly see on this picture that only the definition D2 leads to some kind of increasing along the distance in the hierarchy and the distance in the embedding space, which shows somehow that D2 better captures the thematic distance, and that distance in the embedding space, even if not trained for that, can be used as a thematic similarity measure. So we can use it for pruning. Just to illustrate with an example the difference of the organization in the embedding space with the two definitions. So for example, starting from Microsoft SharePoint and retrieving the direct classes, we have this distance with D1, and we have this distance with D2. So we clearly see that in D2 we have a more clustered organization. And for example, content management system, which could be pruned here, is much closer, and so should be kept in D2. So we used three thresholds: one relative distance threshold with an expansion coefficient based on the average distance of direct classes, an absolute threshold for degrees, and a relative threshold for degrees with an interquartile interval. And we got these results where specific highlights can be done. So first, the precision of the degrees threshold are much better for D1 than for D2. But they only apply on a reduced number of classes. So it doesn't matter so much. Threshold on distance are better for D2, as expected from the previous results, and they apply on a huge number of classes. But the precision is good, so we can use, again, distance in the embedding space as a pruning signal. On the kept classes, we have a better precision for D1, but only slightly better, and on the same number of classes. So it's basically equivalent. And finally, we can see that in D2, we prune much more classes, and we keep much more classes than with D1. So we have a completely different exploration of the hierarchy of Wikidata with this other definition. And so D2 allows for a wider exploration with still a good quality. We can also say that distance in an embedding space that was trained for something else than pruning can still be effectively used for pruning. However, some classes are only pruned with degree threshold. So distance does not capture degrees. And the symbolic degree threshold is still necessary to avoid some hugely generic classes. So now that we have a nucleus of a knowledge graphs, we can refine it, improve it. First, for example, by matching units in it to avoid duplicates or to detect more specific units than some others. So for this specific task, we had a motivating application in my PhD studies, which was the pharmacogenomic domain, which studies the influence of gene variants on drug responses. The specific interest of this domain resides in the nature of the atomic knowledge unit, which is an NRE relationship linking a set of drugs, a set of genetic factors, and a set of phenotypes. So for example, the relationship on the right states that patient being treated with warfarin may experience vascular disorders depending on the variation in the CYP2C9 gene. And this knowledge in this domain is scattered across three main sources. So one specialized databases, which is from JKB, the biomedical literature, from which we can automatically extract knowledge, and electronic health records of hospitals, from which we can mine observational knowledge. And so there is an interest in automatically matching these sources to offer a consolidated view of the available knowledge to some hospital practitioners, for example, or to the curators of Farm JKB, which consolidate the base by reading the literature. So let's take some example. We have these relationships extracted from several sources, and we want to align them. For example, we may want to identify identical ones with some heterogeneity problems. So for example, coumafen is the French for warfarin. Hemorrhagie is the French for bleeding. In a specificity of this task, we also want to identify more specific units than others. For example, this one is more specific than this one because bleeding is more specific than vascular disorders, which is in turn more specific than not knowing the phenotype, because, for example, the extraction algorithm has missed it. The specific variant of the gene is more specific than the gene itself, and so on. We may also want to identify relationships that are not strictly compared, but somehow related. So for example, adverse reaction of warfarin is somehow related to vascular disorders. So this is the task. And compared to what is usually performed in the ontology matching community, it's a bit original because we have some NRE knowledge units. And between them, we want different alignment degrees or different alignment levels. And so there is first a challenge to represent such NRE units. So in the semantic web standards, there are only binary predicates. And so we need to reify the unit itself into a node here, which is linked to its components through binary predicates. So for example, the causes predicate. And so the unit itself becomes a node with its components as neighbors. So we extracted and represented this way more than 50,000 units of pharmacogenomic knowledge in a knowledge graph that is available online to reuse. And our task comes down as follows. From the representation, we want to compare units based on their neighbors. And so this is called a structure-based approach. So we want to take each pair of units, compare their neighbors, and conclude on their similarity. And again, we want to be able to identify different types of alignment between them. So we tested with 4 sources. So the 4 sources of relationships extracted and represented in pgxload. And we developed a first rule-based approach, variously concluding on the equivalence between the relationship. So for example, some that are equals, equivalent, one being more specific than the other, the two being comparable, or the last rules, the two being somehow similar based on some similarity threshold and aggregation of neighbors. And this first approach led to these results where only rule 5 outputs inter-source alignments, which highlights that we are missing some mappings to be able to compare the units between them. And there is a need for a flexible comparison, more flexible than a symbolic one, which motivated us to use the rule results to train machine learning models with the expectation that these models will bring the necessary flexibility. And so again, we used graph embedding and especially graph convolutional networks. Here, with the intuition that the continuous aspect of graph embedding may provide the needed flexibility and may capture fuzzier similarities, be able to deal with missing direct mappings, and so on. So how can we cast this node matching task in the embedding space? Well, this can be a link prediction task. So for example, using the embedding space to predict same as links between pairs of nodes. We could use a node classification approach, which only works if we know beforehand the number of equivalent classes, which is not the case here. And so we considered the node clustering approach. And the learning task then becomes to learn node embeddings such that similar nodes have low distance between their embeddings. And in this specific task, we wanted to study what is the interplay between domain knowledge and deductive reasoning inside the knowledge graphs, and the graph embedding space that is learned on the graphs for matching. So we start from our knowledge graphs with some existing alignments, same as broad match related output by the rules. Because we want to perform node clustering, we have to compute goal clusters that we want to reproduce and transform the graph considering domain knowledge. So to compute the goal cluster, what we did was just to compute the connected components based on the alignments output by the rules. And we have 7 settings, each one considering or not some results. So for example, in C0, we consider all the possible alignments, and nodes that are linked with these alignments are in the same goal cluster. So for example, all these nodes are in the red clusters in C0. In C1, we consider all the alignments with the exception of results from rule 3. And so, for example, this node here, which was in the red cluster in C0, will form its own cluster in C1 because it's linked through an alignment that is not considered anymore. And then for C2 to C6, we just consider one relation at a time. So only C0 and C1 are the most complicated cluster settings because we mix different alignments within the same clusters. And we also transform the graph considering or not some reasoning mechanisms. So G0 is a baseline. We just take the graph as it is. In G1, we merge nodes that are known to be same as. In G2, we had inverse. So for example, if we know that R3 is the inverse of R2, we add the edge. In G3, we compute the missing edges from the hierarchy of predicates. So knowing that R1 is a subpredicate of R2 leads us to add R2. In G4, we compute the transitive closure of the subsumption relation. So knowing that I is of type J and J is of subclass of K, we add that I is of type K. So each of these graphs consider different reasoning mechanisms separated. And in G5, we consider all the transformations all together. Now that we have several graphs and several cluster settings, we can learn an embedding space using graph convolutional networks and the soft nearest neighbor loss. So we used graph convolutional networks especially because they compute the embedding of a node by aggregating the embedding of its neighbors. So nodes with similar neighbors will have similar embeddings, which is very well adapted to a structure-based matching where we want to align nodes based on their neighbors. We use the specific loss function, which to the best of our knowledge has never been used before on graph data, and basically just minimizes the intra-cluster distances and maximizes the inter-cluster distances. So basically what we want to do. And then on the learn embedding space, we apply a clustering algorithm and compare the clusters with the cluster initially, the initial goal clusters. And so what were the results? So when we compared G0, so no inference, no knowledge, and G5, all inferences, basically domain knowledge is helpful on C0 and C1, so the most complicated cluster settings where we have different alignment relations considered, because there is a consistent improvement with the G5. In all the other settings, there is no such homogeneous improvement, but there are more simple settings with one alignment relation each. And remember that G5 is consider all possible inferences, but which one is actually helpful between all that are considered? And so we tested with goal clustering C0 on the different graphs. And what we saw is that all inferences are basically useful, except the hierarchy of classes, which brings a consistent deterioration in the results. However, G5, which again considers all the inference from G1 to G4 included, still leads to improvements and the best results. So other inferences allow to compensate for the deterioration brought by G4. Remember that when we had the graph embedding models, it learned to reproduce clusters that were built from different alignment types. But the embedding model is fully unaware of the different alignment relations at the beginning. But can we rediscover them in the embedding space? So if we consider pairs of similar nodes, are they organized in some way? And the answer is yes. When we compute the distance in the embedding space between pairs of nodes, we saw that the model spontaneously organized the embedding space such that same as nodes, so identical nodes, are very close, while more weakly related ones are further away. And this is somehow a spontaneous emergence of a property in the embedding space. For example, could be considered as a distance as a semantics, because it means strengths of the alignment spontaneously from the model, which advocates for the further integration of domain knowledge in graph embedding models in the input and to measure it in the output. And actually, this measure in the output motivated the next work, which is about predicting link in knowledge graphs and measuring how semantic aware are graph embedding models. So to recap about the link prediction task, it's just to consider a triple, an incomplete triple, head, predicate, and a missing tail, and predict the tail entity. So there have been several approaches, for example, rule-based approaches, graph embedding ones. And the idea for them is to consider a positive triple, so Cristiano Ronaldo played for Real Madrid, remove the tail, and try to predict it. The usual evaluation is based on rank-based metrics. So it measures the ability of the model to predict the expected entity with a high score. So we have the its at k metrics, which measures the existence of the goal truth in the k first entities, the mean rank of the gold entity, or the mean reciprocal rank of the gold entity. But if I give you these two examples, these two models, which have the same rank-based value, it at 5 equal 1, because in the 5 first entities we have the gold truth. Which model is the best according to you? And so basically, we may say that the model on the left is the best because it predicts entities of the correct types with regard to played for. And so even if it's not perfect, because the gold truth entity is only in rank 5, it is semantically coherent, semantically aware. And that's what we wanted to measure with our proposed metrics, which is semat_k, which just simply measure in the k-top entities if they are coherent with the domain or range constraints of the relationship in the triple. And it reflects the semantic validity of predictions. We proposed 3 flavors, depending on the existence of an ontology or not, and the possibility of a class hierarchy or not. We tested on several datasets, several models. And basically, what is important to know here is the different families. So geometric ones, trans-E, trans-H, semantic matching ones, decimal, convolutional ones. And we obtained some results with some takeaway messages. The first one being that the best models in terms of rank-based metrics are not the best regarding semat_k, or not necessarily. For example, the convolutional model conv_E is the best mean reciprocal rank, but is the worst with regard to semat_k. We also have some family trends if we organize models depending on the lowest values of semat_k or the highest ones. So we can see, for example, on the 4 data sets, that semantic matching models are performing the worst. Geometric models in purple, are some of the best, and the best ones being graph neural network ones. And finally, so it's not very visible here, sorry, but if I do that, it's better. Mean reciprocal rank is in green, and semat 1, 5, 10 are red, blue, and purple at the top. And here are the training epochs. And what we see is that models are increasing in rank-based metrics, but being stable with very high value at the beginning of SEM, or sometimes decreasing. So the 2 takeaways are that agnostic models of schema are able to learn domain and range relations, and sometimes at the very beginning of their training. But there seems to be a trade-off between their semantic awareness and their ability to predict the goal truth entity. So can we do better now that we can measure post hoc their semantic awareness? Can we use semantics to improve their training? So following the post hoc measure using domain and range, we used that in the training to integrate ontological information in loss functions. And using the same kind of constraints, we can have 2 different sorts of negative triples. Negative that are plausible because they are valid with regard to domain and range. So for example, Cristiano Ronaldo played for Inter Milan. It's a negative, but it could be a positive because it's valid. And some that are semantically invalid, which are true negative. So Cristiano Ronaldo played for Coca-Cola. And just as a side note, this is some way to tackle the open world assumption in the training, because we have some plausible training, a plausible triple, not in the knowledge graph, but plausible, and some that are true negative, so could never be in the knowledge graph. And we want to input in the training a differentiation between these 2 sorts of negative: semantically plausible negative triples and semantically invalid negative triples, and measure the impact of this semantically enhanced training in terms of rank-based metrics, but also semantic metrics. So we considered some of the 3 mostly used losses in training link prediction systems, and we improved them with semantic introduction through one unique semantic factor, which we called epsilon. So for example, in the pairwise hinge loss, the idea is to make a positive triple far from a negative triple with a margin gamma, which can then be modified by a coefficient being 1 if the negative triple is semantically invalid, or a bit smaller than 1 if the negative is plausible. So we organize the semantic space such that we have positive triple, semantically valid but negative triples, and further away, semantically invalid ones. For the binary cross-entropy loss, where we have a label function of 1 if the triple is positive or 0 if it's negative, we just extend it by 0 if the triple is negative and semantically invalid, and epsilon if it's negative and semantically valid. For the pointwise logistic loss, we use a probability to consider the semantically valid negative triples as positive. So these are 3 possibilities to input semantics within losses. And we tested on a huge number of embedding models and data sets. What we can see basically is that in terms of semantic values, we always have better SEMAT10 values with the semantic training, which is basically great because this was the purpose of the training, being able to differentiate between semantically valid and semantically invalid ones. So good. But we also have an increase in rank-based metrics in 79% of the cases, which means that in injecting ontological information in the training not only improves the semantic awareness of models, but also improve them in predicting the goal truth entity. And just to highlight some very clear cases, for example, we can have some improvement by 30% in semantic values. And so this is one work to advocate again for the further interactions between domain knowledge and graph embedding models, which are now mainly design agnostic, but should include ontological information. So these are works where we intertwine domain knowledge and graph embedding, but we do not consider human utilization of knowledge graphs. And in the last work, where I'm focusing on mining and applications, I want to consider an explainable AI approach where the human is targeted. And especially, we investigated the biological mechanisms behind the occurrence of adverse drug reactions with explainable AI and knowledge graph mining. So, adverse drug reactions are usually statistically characterized, but the molecular mechanisms behind them are unknown. On the other side, we have some expert classifications of drugs as causing or not ADR, and some additional knowledge in knowledge graphs, which is interpretable by humans. And can we use this interpretable knowledge to provide some explanations of adverse drug reactions? And are these explanations biologically founded? That's what we tested with 2 expert classifications of drugs causing or not some liver injuries or cutaneous reactions. So we aligned the drugs with our knowledge graphs, pgxload, and we extracted features to characterize them. So their neighbors, their path, and their path patterns. So what I mean by that is considering some seed nodes in a knowledge graphs, N1 and N2. We extracted features such as neighbors, so V1, which characterizes both N1 and N2, and V2, which only characterizes N1. Path, so for example, P1, V2, P2, V3, P3, V6, which only characterizes N1. And that's why we needed to generalize paths into path patterns. Because if we consider N2, we have one similar path, P1, V4, P2, V5, P3, V6. So we need to be able to generalize intermediate nodes, for example, with the ontology, because V2 and V4 both instantiate T1. And so we need to be able to extract path patterns such as P1, T1, P2, T3, P3, V6. So of course, based on the ontological depth, there is a combinatorial explosion in the number of patterns. So we provided an algorithm to alleviate some scalability issues in this pruning. And once we have these different features for drugs causing or not adverse effects, we trained two classifiers to distinguish drugs causing or not the adverse drug reaction. We used some white box classifiers, so decision trees, from which we were able to extract the most discriminative features. So we have white box classifiers, and we have human interpretable features because they are extracted from knowledge graphs. And we can then ask experts to measure their explanatory power. So the evaluation is two-sided. We have the accuracy of classifiers, which is good. So we are able to reproduce with a fair fidelity the classifications of drugs causing or not side effects. And we have the human evaluation on the explanatory aspect. So are features carrying biological reasons of the occurrence of side effects? And the answer is again yes. In most cases, experts agree that the most discriminative features are potentially explanatory, biologically explanatory of the occurrence of side effects. So can we do more? For example, with more sophisticated approaches, graph neural network, maybe to improve the performance in terms of accuracy at the expense maybe of the explainability. So to conclude, my work revolves around these different steps of the knowledge graph lifecycle. There are several perspectives to consider. For example, other raw sources to build knowledge graphs. I've not talked about texts. I've only talked about aggregating knowledge graphs using tabular data. But there are some interactions between tables, knowledge graphs, and texts. And this is the purpose of the Ecladata national projects, whose I'm the PI, to conjointly use these three sources to extract and refine all three all together. I've talked about matching units, but how do we validate them? For example, if a source is contradictory of another, which one do we keep in the knowledge graph? How do we decide? This is again the subject of a PhD thesis and also of the Ecladata project. And finally, on the neuro-symbolic interactions, we advocate for the further interaction of domain knowledge and machine learning models. But there are also other types of reasoning, and one of which we will explore in the AT2TA project, which is analogical reasoning. So that's it for my talk, and just before ending that, all the data and the code are available in Open Science Perspective on my GitHub, so feel free to reuse codes and data. Thanks.